In this video, we'll explore the concepts of kernel mode and user mode, which are essential for understanding how operating systems manage privileged operations and maintain system stability. This is about privileged operations and dual-mode operation in operating systems. Dual-mode operation is a fundamental concept in operating systems where the CPU operates in one of two modes, kernel mode and user mode. Kernel mode, also known as supervisor mode or privileged mode, grants the operating system full access to the hardware. In kernel mode, the operating system can execute any instruction and access all memory areas, giving it direct control over hardware resources. User mode, on the other hand, is a restricted mode in which applications run. Applications in user mode have limited privileges, meaning they cannot execute privileged instructions or access arbitrary memory locations. Instead, they must request operating system services through system calls, which prevents direct hardware manipulation and ensures system stability. Mode transitions occur when the CPU switches between user mode and kernel mode. This transition is typically triggered by events such as system calls, interrupts, or exceptions. When a user program needs to perform a privileged operation, it initiates a system call, which causes the CPU to switch from user mode to kernel mode. The operating system then handles the request in kernel mode, with full access to hardware and system resources. Once the operation is complete, the CPU returns to user mode, and control is passed back to the user program. Similarly, interrupts and exceptions can also trigger mode transitions, allowing the operating system to respond to hardware events or handle errors in a controlled manner. Privileged operations are specific instructions or actions that are restricted to kernel mode, meaning only the operating system can execute them directly. These operations typically involve direct access to hardware or critical system resources, and allowing user programs to execute them could compromise system stability and security. Some common examples of privileged operations include input, output operations and device control, memory management operations, timer and interrupt management, and CPU state and register control. By restricting these operations to kernel mode, the operating system can maintain control over system resources and prevent unauthorized access or manipulation. A system call is how a user program requests a service from the operating system kernel. Imagine a user program needs to read data from a file. Since user programs can't directly access hardware, it can't directly perform the read operation. Instead, the program executes a system call. This system call traps into the kernel, switching the CPU to kernel mode. The kernel then validates the request, performs the file read operation using its privileged access, and then copies the data back to the user program's memory. Finally, the CPU switches back to user mode, and the user program continues its execution, now with the data it requested. Modern CPUs offer special instructions and mechanisms to ensure these transitions between user and kernel mode are secure and efficient. Memory protection is a critical aspect of dual-mode operation, ensuring that user programs cannot access or modify memory belonging to the kernel or other processes. To achieve this, memory is typically divided into two main regions, kernel space and user space. Kernel space is reserved for the operating system code and data, while user space is where user applications run. When the CPU is in user mode, it can only access memory within the user space allocated to the current process. Any attempt to access kernel memory or memory belonging to another process will be blocked by the Memory Management Unit, or MMU. This hardware component enforces memory boundaries based on the current CPU mode, preventing unauthorized access and ensuring system stability. Dual-mode operation relies on hardware features built into the CPU to enforce privilege levels and memory protection. One key component is the mode bit, a special bit in the CPU status register that indicates the current privilege level, whether it is kernel mode or user mode. The CPU checks this bit before executing privileged instructions, generating a trap or exception if a user program attempts to execute a privileged instruction in user mode. Additionally, memory protection mechanisms, such as the Memory Management Unit, or MMU, enforce boundaries between kernel and user memory spaces using page tables. The mode bit is set by hardware during interrupts, traps, and system calls and cleared when returning to user mode. Dual mode operation provides several protection benefits, including preventing user programs from accessing critical resources, isolating processes from each other, protecting the operating system from malicious or buggy applications, and ensuring system stability and reliability. Mode transitions occur during system calls, interrupts, and exceptions, allowing the operating system to handle privileged operations and respond to hardware events. Hardware support for dual mode operation includes a mode bit in the CPU status register, privileged instruction checking, memory protection mechanisms, and interrupt handling mechanisms. Examples of dual mode operation in practice include ring protection in the x86 architecture, supervisor and user modes in ARM, hypervisor modes in virtualization, and protection keys in modern CPUs. Dual mode operation is a fundamental concept in operating systems that provides the foundation for security, stability, and resource management in modern computing systems. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.